Now let's consider the question of how we can determine if a linear time invariant system is stable by observing its impulse response. Okay. So what we have here is a linear time invariant system, and the impulse response of the linear time invariant system is h of n if it's a discrete time system, or h of t if it's a continuous time system. And what we want to know is if the system is stable or not. Now recall the definition of a stable system. A system is said to be stable if every bounded input produces a bounded output. So what we are trying to do here is to see whether we can transform this condition for stability into a condition on the impulse response, so that we can say if the impulse response satisfies this condition, then we can say that the system is stable. Okay. So again, let's begin with the relationship between the input and the output, which will be given by the convolution sum. Okay. Now what we want is the following. We want y of n to be bounded if x of n is bounded. Okay. Now notice that the condition on x of n being bounded is the same as saying x of n minus k is bounded. Okay. Or if the input signal x of n is bounded, it means the value of x of n at every n is bounded. Okay. All right. So now let's look at the magnitude of y of n. Now the magnitude of y of n is simply the magnitude of summation h of k, x of n minus k. Okay. Now what we know is this: the magnitude of a sum of signals has to be smaller than the sum of the magnitudes. Right? It's easy to see this in the case when x and h are real. So essentially then what is happening is, if I were to sum a few real numbers and then take its absolute value, when I sum the real numbers, some of them can be positive and some of them can be negative. So I may end up with something that is smaller than summing the absolute values of each of those real numbers. Right? That's all that's going on here. Okay. Now what we can do further is the product of, or the magnitude of the product of these two signals is the product of the magnitudes. So this is equal to summation magnitude of h of k times the magnitude of x of n minus k. And what we know is that x of n minus k is bounded. Now what does it mean for a signal to be bounded? Well, since x of n is bounded, we know that the magnitude of x of n minus k is smaller than some number, and let's call that m sub x, because it has a bound, right? So what that then means is that the magnitude of y of n is less than or equal to the bound on x times the sum of the magnitudes of x of k. Okay, this is nice because it gives us the condition that we want. Well, if I want y of n to be bounded, now what this expression here says is, look, the magnitude of y of n is smaller than m sub x times something. So if y of n needs to be bounded, then what has to be bounded is this quantity here. Okay. So then the condition for stability becomes this. If the impulse response is absolutely summable. So what that means is, if summation k going from minus infinity to plus infinity of the magnitude of h of k is bounded. Let's call this some m sub h, or equivalently is bounded. Then the system is stable, because then y of n would be bounded. And in fact, it's easy to see that this is a if and only if condition. Namely, if this condition is not satisfied, then the system is not stable. Then we will always be able to construct an input in such a way that the output is unbounded. Okay, so this is the condition which says, if the impulse response is absolutely summable, then the system is stable. Now notice here that we could have replaced the k by n, because this just is a dummy variable here, and then we can express it directly in terms of the impulse response h of n. So if this is bounded, then the LTI system is stable. If not, then the system is not stable. Or equivalently, we can say the LTI system is stable if and only if the impulse response is absolutely summable. Okay, so let's look at a couple of examples just to get more familiar with this concept. Before I do the example, the equivalent statement for a continuous time system is that the LTI system is stable if and only if the impulse response is absolutely integrable. So if I look at the integral of the magnitude of h of t from negative infinity to plus infinity, this quantity is bounded. I don't know why I'm not able to erase that. Okay, there we go. Okay, so let's look at a couple of examples. First, let's look at the system whose impulse response is given by h of t is equal to u of t, which is the unit step function. So is this system stable? Well, if I plug this h of t into this expression here, I see that integral negative infinity to positive infinity of the magnitude of h of t dt is integral 0 to infinity of 1 dt here, which is clearly not bounded. Okay, so the system is unstable. And in fact, we could have arrived at this without using this let us just double check to see whether it makes sense for the system to be unstable or not. And to see this, notice that the output y of t is actually given by, let's look at, it's going to be the convolution of x and h, right? So it's x of t, h of t minus tau d tau. Or equivalently, let's just graphically think of a signal. Let's say I have some signal x of t, or let me think of it as x of tau, and my h of tau is the unit step function. So what is h of minus tau? H of minus tau is a flip of this, and so this is h of minus tau, right? To compute y of t, what I need to do is I need to shift h of minus tau by t units to the right, in which case I will get some function which looks like this. Basically, I will get some function which looks like this. And then I have to multiply these two signals and then integrate them. When I do that, notice what I'm going to get is that I'm going to get y of t to be integral from minus infinity to t of x of tau d tau. Well, what that really tells me is that the system whose impulse response is h of t is equal to u of t is actually nothing but an integrator. And we already looked at a few examples in class before. One of them was the integrator, and we knew that the system is unstable. Because if my input is, for example, the all 1 signal, the output becomes unbounded. So we knew before that this was unstable, and now based on the impulse response of this, we're arriving at the same result.